That is, we understand that d by dt from minus infinity to plus infinity, psi mod whole square dx is equal to 0. Or in 3 dimension, if I write, I can write d by dt minus infinity to plus infinity, psi mod whole square d tau is equal to 0. What does psi mod whole square represent? I've told you it many a times. Psi mod whole square represents the probability density at point, let's say, x and t, and psi mod whole square dx represents probability of finding the particle, in the interval, x comma x plus dx and time t. And if you integrate this thing, you'll get the total probability. So if you integrate this thing, let's say from minus infinity to plus infinity, it suggests that it should be some finite valued answer. I'll say less than infinity, and more precisely, it should be 1. Okay, this is all that you already know. Now, this also one of the another implication yesterday also I told you that it also implies preserving of the normalization constant. That is, if you find a normalization constant at t equal to 0, let's say a, then it remains the same at any future time. Because after all, understand, it's only after you know that if I take the norm of psi and it is equal to 1, from this only you get the value of a. And if I'm saying this norm of this particular thing is 1 throughout, then obviously, and it does not change with respect to time. It does not change with respect to time. This is what we've done yesterday. Therefore, if we normalize our wave function at t equal to 0, it remains normalized forever for all future times. So this is at times referred to as, this means this particular statement. So this particular statement is referred to as global conservation of probability. Global conservation of probability. This is called as the global conservation of probability. This is one. Okay. Now, there happens to be a local conservation of, you can say, local conservation of probability, just like fluid. So local conservation of probability, it almost follows the same trend as that of fluid. And as I go along, I'll show that a famous equation of continuity, which is in fluid, appears exactly when we actually investigate this conservation of probability further. So it can be said that, I'll explain all these things, don't worry, that probability does not jump, like probability does not jump from one location to another. That is, if I'm saying with respect to x, one location to other, rather it flows as if it is a fluid. In other words, if I'm saying that there is, let's say, with respect to fluid vector, you can think of fluid velocity vector, you can think of, or you can say velocity field. Okay, so if there is a cross section And if I'm saying that the fluid is coming inside, then there is some increase in this area, increase in, you can say fluid content or in this area, which is actually, which actually corresponds to decrease somewhere. Okay, so understand that if there is a constancy, if there is a constancy, let's say if I'm saying that my probability, the total probability remains conserved, so total probability is constant. So if it is an increase in some region, it should correspond to decrease in some region. It should correspond to decrease in some region. Okay, so this is how probability behaves. So this is what we are going to investigate today. Okay, so I will write it here so that you get the point. So as you can say, as time evolves, from, let's say, t equal to 0, the probability of finding the particle in some region may increase or decrease, but total probability remains constant. Remember, may increase or decrease. Okay, so if the probability increases in some region, it should decrease in some other region. It should decrease in some other region. So if there is an inward flux, so there must be an area from where this flux is getting released. So it should decrease in some other region. Why? Since the total probability, of finding the particle, anywhere in the space is equal to what? Unity. Is equals to unity. Is that clear? So this is one thing that you should just for the sake of writing, I have written, and we'll see. Just skip. Okay, so this is one thing. Now, another thing that now let us start with this, whatever I have written. So basically, what happens is that probability flows from one region to another. Similar equation you'll also find in electrodynamics also as we'll go along, but probability flows from one region to another as if it is a fluid. So this is the basic physics. You can say a little bit of physical thing. Now we'll see what is happening. See, so if you remember, if I now let me write one more thing. So for example, I know that my Schrodinger equation is what? My Schrodinger equation is minus iota h ket del by del t. Then I can write is equals to h ket psi. So I'll not use h ket. So I've not used h ket till now. So I'll use it in the, what you can say, in one dimensions only, and then I'll take this particular thing to 2 dimensions, so that to 3 dimensions, so that you get to know what is the 3-dimensional equation as well. Okay, just give me a minute. So I'll put it this way, so it becomes easy for you to understand. Give me. Okay, so I'll use a three-dimensional equation. That would be easy for me. But that's okay. Let me first write this first one-dimensional equation so that minus h ket square upon twice n, and then you have this del square psi upon del x square, and then you have, I think, vx, v and psi. And know that this is a constant, right? Or you can say this is not constant, this belongs to real. So it's not that this is imaginary. We are taking the case of constant. Okay. Because we have seen that if V belongs to complex, or if we are talking of some unstable particle where there is a decay or or decrease, or you can say decrease of probability with time, then you've seen already that in these cases the probability does not remain conserved, rather probability behaves as if it is a function of t. Okay, so this we have seen. So we are taking real here potentially is a real function. So fine, this is all good. Now the same equation I will write in 3 dimensions. So if I have to write the same equations in the 3 dimensions, then how will I manage the same? So this is instead of derivative, what would come instead of derivative? There would be a I'll write it in this fashion so that you'll be able to get what I want to say. There it is. Okay, this is here. So instead of this thing, I can write this way.
हेलो सर।
हाँ बेटा,
हेलो।
हेलो।
हाँ सर, मैं कह रहा हूँ कि हेलो।
हाँ हाँ बेटा बोलो।
हाँ सर, मैं कह रहा हूँ कि वो भी जो है वो कॉम्प्लेक्स या रियल है?
ये तो रियल है. If it is complex, then yesterday we saw that if I add this V naught minus iota gamma t, iota gamma, then for this particular values, your probability does not remain conserved. Rather, it behaves as if it is a function of t. So we have to take it in real terms. Is that clear?
Okay, okay sir.
Because if I don't take yesterday we did now this particular case, so I'm excluding these cases. So this is not it. So we are not taking these cases. So we are not considering these cases. We are considering when the potential function is a real function. Is that clear now? ये तो अभी clear हो गया. Is that clear now? Yes. Should I go ahead now? So okay. So instead of writing this, so what I'll use, so del by del psi by del t is equal to as happened. So this is equals to minus h ket upon 2m iota, and instead of that I'll write this del square psi upon del x square, and then you have this v psi. Okay, so this is your one-dimensional equation. So if you want to write the same equation in 3 dimensions, so that at times when I say that flow and flux, things like these, so taking a 3-dimensional case makes much of the understanding. So this is your one-dimensional case. Psi upon del t, this is fine, minus h ket square upon twice m, you have this del square psi upon del x square, then you have this v, let's say as a function of x, and let's say psi. If I want to write this equation in 3 dimensions, this would be del psi upon del t, and then you'll have this minus h ket square upon twice m, and then you will have del square psi as a function of, let's say 3 dimensions, so let's say r and t, and plus v as a function of r and t, and then you have this psi. Right? This is fine. If I'm not making any mistake till now, this is fine. Let's say this is equation number 1. Let me take the conjugate of it. So what I'll get, minus iota h ket del psi upon del t, del psi star. And if I've taken conjugate throughout, I've taken conjugate here as well. So this will become del square. And here you will get psi star, and then you will get r vector comma t. And then I have kept this as a real real function only. So this will be okay. This is your 2. Both of them are here. Now, what I can do, um, I can multiply this by, I think, psi star, and I can multiply this by psi. Okay, I can multiply this by psi star, I can multiply this by psi. So if I do so, what I'll get iota h get, and then I will have this psi star, and let's say I'll subtract this also. Del psi upon del t, and then plus iota h get del psi star del t. Okay, so this is one thing here. And if I take this up, so this will get cancelled because psi mod whole square, and here also psi mod whole square, v is multiplied to them. This will get cancelled, and this will prevail. This will prevail anyhow. And what it would be equals to? It would be equals to h ket square upon twice m, and then you have, I think there would be some psi at first, and del square psi star, and then minus of h ket square upon twice m, and then you have, I think, psi star del square psi. I hope it is clear now. I think now it makes some sense. Just take iota h get common here. It will be equals to, I think, just think about this. This will be equals to del by del t of psi star and psi. And here it is. If I take a minus of h get square upon twice m common, then I will get psi star del square psi, I think, and then minus of psi, and then I think del square psi star. I think now it is fine. I think now it is fine. Okay, so this is what I have got. This is what I have got. If you want to simplify it, we can do that also, but let us write it in this fashion. So other ways I can write this way. I can write in this fashion. I will write it as, I'll write it as this. Understand, this is your probability. This is your probability density, sorry. This is your probability density plus h ket square upon twice m. And I think you will get, I think 1 upon, I'll write it right here only once. And here you have this psi star del square psi minus psi del square psi star. And this is equal to 0. If I divide by iota h get, what I'll get? I'll get del by del t of rho. What is rho? Rho is your, I'll write it here, rho is your probability density. So psi star psi, this is your probability density of finding the particle at point x and t, let's say, or r vector and t here. Since we have taken the 3-dimensional case, so it represents the probability density at point r, at r vector at time t. Plus, if I divide it, so I'll get 1 upon, so this will become h get, and you will have to iota division. You multiply up and both above and below. So I think at the end you will get iota h get upon twice m. There would be a negative sign, I think. So I'll shuffle that sign. So you will get, I think, this. And this is equal to 0. I hope it is now clear. Okay, is that clear? Yes or no? Is there any doubt in this? So I don't think there is a doubt here. So I think this equation, this is one equation. And yesterday also we did one thing. And just remember this equation. Let's say this is your final equation. Let's see equation number 4. Just forget about this. So I think I was making some, there was some sign error in this. I don't know what. See, if I was subtracting this, then I don't know what is a mistake somewhere. I've made a mistake here. So forget about this. Just think about this. So this is one thing that you should remember. And we'll come to this. Now just think about this particular equation. And if I try to write it in 1 dimension, or let's say 2 dimension, or if I expand this up in 3 dimension, I'm writing it here, let's say here. Okay, so let just write one of the component, let's say x component. So it will be psi del square psi star upon del x square minus psi star, and then you have del square psi upon del x square. Okay, this is one thing. And if I want to write this, can I not write it in this way? It is equals to del by del psi of psi. Can I not write in this fashion? So if I write this particular thing, see, I have just taken the x component here. Just taken the x component. So x component will be like this only. I'll take a derivative. So if I take the derivative, I'll get back to this. I will get back to this. So if I want to write it in 3 dimensions, so I think this will be del rho upon del t plus iota h ket upon twice m, and then you have this. I'll write del by del x of. This is a long expression. I think I will have to have some space in there. Okay, let me see. Even if I don't have space, so I'll write this way: psi, and then you have this psi star, and then you have this del psi upon del x plus iota h ket upon twice m. You can write y component, which is del by del y, again psi, and I think z component also. Okay, equals to 0. Equals to 0. So if I write it in a little bit of a compact form, then this will be equals to del rho upon del t plus del. So if you just think about this, so if I take a divergence, then what I can write this entire thing, I can write this entire thing as del dot some j vector, which is again a function of r and t. And what this j vector is, this j vector is nothing, but it is equals to, I think, iota h ket upon twice m. And see, this entire, if I want to write, I will write this entire thing as psi, gradient of psi star, sorry, grad of psi star. So instead of, in the first it is x, in the second it is y, and minus of psi star. So this is how you write. Now, since you're famous, equation of continuity, I think. And it is quite often used in hydrodynamics and you can say electrodynamics also. So this is one thing. Is that clear or not? I think this is clear. This particular thing is called as probability current density. This particular thing is called as the probability current density. Now, if you actually, yes.
Sir, this density word, it might be used because जैसे हम करंट लीनियर चार्ज सरफेस चार्ज और वॉल्यूम चार्ज में डिवाइड करते हैं
हाँ,
तो वैसे प्रोबेबिलिटी भी हम 1 डायमेंशन 2 डायमेंशन या 3 डायमेंशन में सिस्टम के अकॉर्डिंग डिवाइड करेंगे तो प्रोबेबिलिटी फ्लो या तो किसी एरिया में होगा डायमेंशन के अकॉर्डिंग या किसी वॉल्यूम में होगा तो शायद इसलिए डेंसिटी को दे रहे हो वहां से
हाँ, हो सकता है सही. That is because the guy asked you, Deepta asked this question right now, that why density has been used. It looks as if it is first order derivative, and it looks as if it is a probability current at first. So he says that why density has been used. And right now I don't have a correct answer to this. So
या दैट्स व्हाट बिकॉज़ ऑफ करंट की डेंसिटी जैसे हम लीनियर चार्ज डेंसिटी सर्विस चार्ज डेंसिटी लेते थे कलर क्योंकि करंट एक मतलब डायमेंशन के अकॉर्डिंग एरिया में या वॉल्यूम में लीनियरली फ्लो कर रहा है तो उसके लिए हम डेंसिटी डिफाइन करते थे तो वैसे प्रोबेबिलिटी भी तो डिफाइन कर सकते हैं
Okay. So I got your
मतलब
point. हाँ
मतलब ये हाँ
हाँ, I got your point. Let's say you are
प्रोबेबिलिटी
saying
वैसे भी डिफाइन
कि
होती
अगर 1 डायमेंशन में है तो बाय लेंथ हो गया, और 2 डायमेंशन में तो बाय एरिया
है
हो
यस
गया,
सर
3 डायमेंशन में हो गया तो
यस
बाय वॉल्यूम हो गया. तो इस इन दिस सेंस यू आर सेइंग दैट it may be called as the probability current density, right? This is what you are suggesting. Okay, so I'll find an answer to this. Don't worry. Right now, let us do a few questions regarding this, and then we'll see why it is called as that. But usually, I found this written as probability current in some books. In some books, you will find this as written as probability current density also. So we'll see. Don't worry. One more thing that you can think of is so basically what I can do is, so I'll do one thing. So one more thing, just an observation I'm giving you, just an observation. See, if you take the derivative of this rho over, let's say, entire volume tau, what it is going to be? It is going to be del by del t of psi star psi, and then you have this thing. So basically, it is equals to minus of, I know from above equation, it is equals to minus of uh, divergence of del dot, sorry, divergence of j vector, and then you'll have theta. Is that clear? Now from divergence theorem, Gauss divergence theorem, we know that this is equals to what? This is equals to j vector dot n cap ds. Okay, so what is happening? Del by del t of integration of rho r vector dt d tau over entire volume is equals to negative of j vector dot n cap ds. Okay, this is one thing that you can keep in mind. Also, just think about one thing, one case that let's say if I expand my space, or let's say if I want to do this integration all over space, then this will be equals to what? Then this will be equals to what? All over space means r vector mod will tend towards infinity, and as r modulus tends to infinity, both psi and psi star would tend to 0, because this is from your this is the basic postulate. Okay, so let's say if your S is the surface which encloses this volume tau. Let's say S is the surface which encloses volume tau, and we are expanding this volume. We are expanding this volume. If we are expanding this volume, then as I expand, the psi goes to 0, psi star goes to 0. And if this goes to 0, I know that my j goes to 0. And if my j goes to 0, that is, I'll write it here, my j goes to 0. So this particular fellow would go to 0. And if this goes to 0, it implies again the same thing. It implies again the same thing, that in entire space, if there are no as such sources, or let's say not the cases of decays, okay, we are talking of stable quantum particle. If there is as such no source or sink, your total probability again remains constant. So it again gives you the same statement. Okay, so this is one thing that I wanted to mention. Now, just think of this thing. So let us take it in one dimension. Probably that may make sense. Okay. So one more thing, let us do some question also, don't worry. But let us first think about this thing. The same equation, if I want to write in one dimension, what it would be? So I'll write it in this fashion. In one dimension, it would be j vector. If I'm writing in x direction, it would be equals to iota hget upon twice m, and then you will have the psi, and then del psi star del x minus psi star del psi upon del x. And if you want to write x cap, you can write x cap as well. And what I can write my del by del t. So instead of del by del t, I'll simply write del t. Probability as a function of, instead of r and t, I'm writing x and t. And then instead of del by del x, I'm just writing del x so that it represents this is equal to 0. Now let us integrate this. And I'm going to integrate this. Integrate this with respect to x from, let's say, x0 to x1. And let us in time t. So what will happen? This will be like, when I'm integrating, I'm differentiating with respect to t. So I can take partial derivative outside and also take it inside if I feel like. But right now I'm integrating with respect to x, and then plus this will become del j upon del x, and then you have this integration with respect to x. You have this x1 equals to 0. Now, if I write this, what it is going to show me? It is going to show me that del t means del by del t, tx comma t dx is equals to j of x0 minus j of x1. So let's say this is your x0, and let's say this is your x1. So so I can write it from from here, that the change in probability, or you can say rate of change. You can say, let's say, if I want to write the rate as increase, let's say this is positive. So rate of increase of probability is equal to what? Is equal to the difference of probability current. Probability current. So basically, what probability current is entering here and what probability current is leaving here, this difference marks the rate of increase of probability. So basically what is happening in this particular interval, your probability is increasing. So it is obviously it is equals to what? It is equals to the net. You can say as if it is like flux, or you can say as if it is like some probability moving as if it is a fluid. So probability current here and probability current here, you just take the difference. That will tell you what is the rate of increase of probability. In 3 dimension, if you want to visualize, probably that will give you a little bit of more understanding. In 3 dimension also, we did the same. We wrote this thing as del t, and you had this, I think, t as a function of r vector in t here. And instead of dx, I will use, let's say, d tau, or let's say d cube r vector. And let us integrate it. Plus, instead of this guy, I will write so what I can write. So here it is like this way. I'll use this form then. Okay, so I'll use this form. So I'll use this form in 3 dimension. I'll use this form. So instead of writing this, I can write j vector dot ds entering in some surface S, or let's say if I'm saying volume omega, I'll use d omega. D omega is what? D omega is represents the surface enclosing the volume omega. So this is how I can write by, again, the same equation in 3 dimensions. Now, what it is equals to, it is equals to, if you remember, E vector dot ds. What is E vector dot dx? Usually it represents, when we say in electrostatics, just think about this. This represents some kind of flux. This represents some kind of flux. I'll write it here. This represents some kind of flux. Flux of what? Flux of probability current. Okay, so rate of increase, if I take there, it would be negative. It would be negative. So if I'm saying rate of increase of probability in some volume, let's say I've written this, in some volume, this equals to negative of flux. If remember, if you were doing electrostatics, what was negative flux? So if I'm saying that my flux is entering, if my flux is entering, we denote it by a negative sign, and if my flux is leaving, then we denote it by a positive sign. It is equal to the net inward. So net inward flux of probability current across the surface d omega. So again, it implies that if in a volume your particular current, your probability is increasing, then it is equal to what? It is equal to the net inward flux. So basically, this inward flux would be coming from some region. So since total probability is a constant, so in a volume, if probability is increasing in some region, it should have a decrease in some region in order to keep this total probability constant. So this is this also derives from your law of conservation of probability, and we get one important quantity which is usually asked in the exam, and this is called as the probability current density, or at least probability current for now. I'll write. Okay, usually we use word density also. I'll find why it is called density and revert to you tomorrow. But usually this is how it is written, and this is equals to what? This is equal to iota h get. In 2 dimensions I'm writing. In 1 dimension I'm writing iota h get upon twice m, and then you have this, I think, psi, and then you have this del psi star upon del x minus psi star del psi upon del x. At times in books you will find this particular thing being written in this form also. What do? They actually divide it by 2 iota also. So if I divide it by 2 iota, so I'll use this 2, okay? So, and if I multiply again, I'll multiply with iota only. So this will be minus h get upon m, and this is 1 upon 2 iota here. And just think of this. Can I not write it in, can I not write it as I'm writing it here so that you'll be able to get what I'm trying to say? I'm going to write imaginary part of psi star del psi. So what is imaginary part of this? Imaginary part of this would be psi star del psi minus again conjugate divided by 2 iota. Okay, so if I do so, this negative will again get absorbed, and this entire thing would become h get upon m, imaginary part of psi star del psi. So this is how you also define your probability current density. Okay, so why it is called density, I'll find one reason. One of the reasons has been given by Bharat himself. He's telling that it's because that probability we actually, let's say, if there's a charge distribution, so charge distribution depends upon how it is distributed. Let's say it is distributed in 1 dimension, then it is linear charge density, and in 2 dimension it is a surface charge density, in 3 dimension it is volume charge density. Similarly, probability, as if when we were doing in 3 dimensions, when we were doing, I made a figure where I had a volume and I had a surface, and in 1 dimension I was doing it in this fashion, linearly. So probability current entering, probability current leaving is equals to rate of increase of probability in this interval. Here the same thing, the probability current entering through some surface implies the flux of that probability current. Flux of probability current inward implies negative. So basically, the rate of increase would imply that your net flux of probabilities entering into some volume. Obviously, it would be leaving some volume also. So understand that since the total probability is a constant, so probability increasing in some region implies probability decreasing in some other region. So basically, this is how your law of conservation of probability works. And from this, we get this. Now let us take some examples, and I hope you're able to understand or not able to understand. Okay, is that clear? Okay, so good. So now we'll take some examples. So let us first take the case of the plane wave. And a few things I'm going to directly write. So plane wave, the wave function is given by, let's say if I'm doing in one dimensions only, psi x is equal to e to the power iota kx. Okay, and we want to find the probability current density. We want to find the probability current density for this wave function. We want to find the probability current density. So that is equals to J is equal to iota h ket upon twice m. And then you have this psi. And I'll take the derivative of this conjugate. So I'll write the conjugate also. It is equals to minus, sorry, it is equal to a e to the power minus iota kx. So if you see this, either you do this way or you do anyway. So I'll use this. This seems to be more compact form as such. So what I'll do, I'll not write. I'll write imaginary part of psi star. Right side. So basically, psi star is a e to the power minus iota kx into del by del x of this. This is iota k a e to the power iota kx, and then some star. Okay. So there would this would be equals to iota k modulus of a whole square. So instead of this, I'll write this. J is equal to iota h ket upon, sorry, not iota h ket. Here it will be h ket upon m only. So h ket upon m, and imaginary part of this, imaginary part of iota k modulus of a whole square. It is equals to h ket, and then you will have this modulus of a square. You will have k upon m. Okay, and if you want to write the linear momenta, linear momenta is equals to h ket k, and if I want to write it as mass by mass into velocity, I'll write mass into velocity is equal to h ket into k. So this h ket k I can write it as mv. So it will be equals to J will be equals to what? J will be equals to V into modulus of a square. And what is modulus of a square? Just think it is psi star into psi only, because this would become simply like psi star into psi. If you do, this will become modulus of a square. So for a plane wave, the probability current density is equals to what? Equals to velocity into you can say probability density. Now, if I want to take a spherical wave, so how is spherical? What is the wave function for the spherical wave? It is represented by, let's say, if I do it in as a function of r, and I'll write it as a e to the power iota kr divided by r. It is equals to a e to the power iota kr divided by r. This is how I represent my what you can say spherical wave. Is that clear? The wave function for the spherical wave. Is that clear or not clear?
Yes.
Okay, good. So now if I want to write this probability current density, it will be equals to h cat upon m imaginary part of psi star del by del r of psi. So this is how I'm going to write. Okay, so psi star, this will be equals to a e to the power minus iota kr divided by r. This is simply your psi star. And what would be psi? Del grad psi. It is del by del psi upon del r. This will be equals to minus of a upon r square e to the power iota kr plus iota k a e to the power iota kr divided by r. Now, if I multiply this psi star, what will I get? I will simply get minus of a square upon, sorry, this is a star now, so this will be mod a square, and I think this would be r cube plus iota k mod a whole square upon r square. So this, the imaginary part is this, so I'll get j is equals to h cat upon m, and then I will have this k modulus of a whole square divided by r square. So here you will get an expression as h cat k upon m r square into modulus of a whole square. Which is simply equals to, I think if you write it in this fashion, this is velocity divided by r square times the probability current density. No, this is probability density. Is that clear till now?
Yes.
Okay. Chalo. Now let us do one more thing. So that also happens. That is also a good thing to do. Let us take one more case of Gaussian wave packet. Usually Gaussian wave packets are quite used in your quantum mechanics. So let's take third case of Gaussian wave packet. Okay, and let us write the Gaussian wave packet. The wave function as psi x is equals to a exponential of minus of x square upon a square, and then plus iota, let's say some p naught x upon h cat. And I want to find jx vectorially in x direction. So now if I want to find vectorially in x direction, all you need to do is just use x cap also along with that. Okay, so I know that this is equals to h cat upon m, and then imaginary part of psi star grad psi. This is how it is. Okay, so all I need to do is psi star into grad psi and just take the imaginary part of it. So if this is my psi, what would be my psi star? Psi star would be e minus of x square upon a square will remain as it is. Here you will have minus iota p naught x upon h cat. Okay, and if I want to write del psi upon del x, it will be equals to a exponential will remain as it is. I'll write, okay, I'll write once. and then you will have this minus of so if I want to use this, then what I'll get? What is psi star? Psi star is this. So I'll write again A star. I forgot. Okay. So this is A star. Then you have this EXP. And then you have this minus of x square upon A square minus iota P naught x upon h ket times del psi upon del x, which is A exponential of minus of x square upon A square plus iota P naught x upon h ket, and then you have this minus of 2x upon A square plus iota P naught h ket. Okay, so this is multiplied. Okay, I think this is fine. First, we are finding what we are doing. We are doing psi star into del psi upon del x. This is what we are doing. Okay, and this A and A star, if I just take, so it will come out as A modulus whole square. And this fellow is going to come here. So I'm writing it here, minus 2x upon A square, and then plus iota P naught upon h ket. Okay, and then this exponential, both of them get multiplied, and I'll get exponential of minus of 2x square upon A square. And we have to just write the imaginary part of out of this. So we just have to write the imaginary part of so this imaginary part would be simply this. So it will be like P naught upon h ket modulus of A whole square, and then you will have this exponential of minus of 2x square upon A square. And if I want to write the probability current density in vectorial form, it will be equals to h ket upon m times this x cap. Okay, so I think this h cat would get cancelled. So you'll have this h cat upon simply m exponential of minus of 2x square upon minus 2x square upon A square x cap. This is your probability current density in vectorial form for a Gaussian wave packet. I hope it is clear. Now, just try to do one more question. Let's say if my wave function is completely real, let's say I just take one linear combination and I'll show it to you. If the wave function is completely real, then what do you think the current density would be? So let's say I have this wave function. Let's say psi x is equal to e ki power iota kx plus 2 e ki power minus iota kx. And I want to find the probability current density J of the real part of this psi. What it would be? Okay. So if I want to find the real part of this, so let me do it for you. So basically what it is equals to, it is equals to cos kx plus iota sin kx plus 2 times cos of minus kx plus iota sin of minus kx. So it is So basically we want to take first real part. So the real part would be simply 3 cos kx, right? Iota would not, I will not include the term which are attached to the okay. So this is 3 cos kx. And if I want to write the current density corresponding to this will be equals to, this is your psi, and this is your simply psi, and what would be even del psi upon del x would be some real number, which is simply, even if you take the psi star, this will remain the same, minus 3 k sine kx. If you multiply them, they will belong to real number only, and the imaginary part for psi into del psi star upon del x would be simply 0. So therefore, the probability current density would be simply 0. Is that clear? Now, little bit about what you can say, little bit about the dimensions. So I'll write it here. What do you think would be the dimensions of J? What do you think the dimensions of J would be? Okay, so we'll do it anyhow. See, just remember one thing. So for example, I'll start from here. So when we are let us say make it easy. Let us make it easy by doing one dimension thing. So let us restrict to one dimensions, because after all unit would remain the same, right? We have to just think about what are the dimensions of this. So I'm restricted to one dimension, as it means along a line. Okay, now if I'm doing so, what do you think the dimensions of wave function would be? What do you think the dimensions of wave function? See, this is what I was referring yesterday, that if I want to find psi mod whole square dx, this is probability, this represents probability, and this would be some constant. It would be some constant. This is some, I think, unit of length. So what you can expect here? You can expect a unit of L minus half. Only if the unit of this wave function is L minus of half, only then this integration would be some constant. Yes or no? So in order that this probability remains unitless, or this probability remains dimensionless, what you can say, the wave function, this particular wave function, the dimensions of the wave functions are L minus half. Even if you don't get it, and even if you are exposed to even BSc standard quantum mechanics, you know that for an infinite dimensional, for one-dimensional infinite potential well, the wave function is given by root over 2 upon a sine of n pi x upon a. The eigenfunctions are given by this. So it is inversely proportional to a raised to power, what you can say, length raised to power half. So from there also you can do, from here also it is quite clear. Is that clear?
Yes.
Okay. So if let's say you are working in some d-dimensional space, then obviously this will change to, let's say, for example, let's say if you have a cubical box, then for d-dimensional space, it would be equals to L raised to power minus of d upon 2. Okay, but right now let us restrict ourselves to one dimensions, and we'll find that this does not depend upon it. Okay, so this does not depend upon it. So see, psi star into del psi upon del x, this is 1. What would be the dimensions of this? So psi already has a dimension of L inverse, L minus of half. Psi star will also have a dimension of L minus of half. So basically they too will have a dimension of L minus half. And x, the dimension of x is again L. So the dimension would be simply 1 upon L square here. Okay. And I think this is clear. Okay. What do you think the dimensions of h cat would be? You just write this as, I think it will be ml square upon t, I think. You just find it on your own. This is very simple to do. And if you find h cat upon m, then you found that it is L square upon t. So if you want to write the dimensions of this thing, that is h cat upon m psi star del psi upon del x, this will be simply 1 upon time. So this is what yesterday I was referring, but somehow probably I was not able to make it, or some difficulty was there. So overall, understand that this particular thing, this current density, has the inverse dimensions. Like it has the dimension of 1 upon second or 1 upon time. Is that clear? I think this is quite clear now. Okay, so this is one thing, and please to understand that. Okay, so this please understand that basically this probability current density is actually an outcome of conservation of probability only. So this is an outcome of conservation of probability.